So what about, all right, let me introduce some notation now that we've gotten the idea a little bit. If I start with just f, and let me give you one that's not too evil, e, let's say it's e to the 3x. When I find the antiderivative of just a function, I'm not considering this to have been differentiated, because there's no prime on it, right? What I normally do when I step back and there's no prime, I make it big ass f. Or whatever you want to call it, poor guy. So this means big ass f prime is little f. Do you guys get this idea? When I take the derivative of this, I go back this way. So now I'm going this way. Now I'm taking the antiderivative. What would that have to be? Very often, the way to think about it is, what do you get if you take the derivative of this? 3e to the 3x. Is there a 3 there? No. So what must have been out there to kill the 3 that wants to come down? 1/3. There must have been a 1/3 there to kill the 3 that wants to come down. Right? That sounds like that. There wasn't a lady who swallowed fly song. You know that song? Pussy. Thank you. Now, I like it if somebody would think, is it an even bigger F? You give another step? No. You would just have to use the right symbols for that. But normally this is a one-step deal when we use this big F thing. Big F is the antiderivative of little f. That's the notation. Okay, cool. Let's see. How freaky do I want to get here? Oh, all right, let's do this.
Your equation backwards. It said big fx equals f prime. Is that right?
No. Big F is the antiderivative of f, so the derivative of big F is little f. In fact, what do you get when you take the derivative of this? How do you check your work? You take the derivative. Yeah. But I totally understand, because it's the changing gears thing. It's like, well, wait a freaking second. But if you ever see this big ass f in calculus, normally it's meant to be the antiderivative of little f. So you can always check your work. You just take the derivative and see if you get back to where you started. That's how you check it. Okay. So, what if I told you that you had a particle moving with an acceleration? This. And I tell you, the velocity at time 0 is -6. We won't worry about units right now. And the position at time 0 is 9. Can anybody figure out why I would give you this information? What will that help me figure out? Not to check my work. To figure out what C is. If I told you big ass f of 0 was 3, then I could figure out what C would be. I could just set the equation up and solve for C. That's what those are going to do for me. Now, what's the relationship between acceleration and velocity? What do you do to velocity to make acceleration? Take the derivative. So now I'm going to take the antiderivative. Okay, cool. So write that down. Take a minute, write that down. Don't say it. All right. Yes, sir.
So let's write C or
you have to.
Whatever.
Because then the next thing is we're going to use that to figure out what C is.
Oh, okay.
Yeah.
3t squared.
All right, so 3t squared
Plus 2t.
You're thinking too much. 4t.
Plus c.
You would only have to worry about doing something to the coefficient if you had to have a higher power that would have come down, but there wasn't anything there to have to do. So how do I figure out what that C is? Use this, and this is what we normally call this our initial conditions. It's your initial conditions. Sometimes it's called boundary values, depending on what level of stuff you're doing. But initial conditions work for most things. So what's V of 0? That's going to be, well, that's too easy. C, which is -6. So now I know C is -6. That was beautiful, right? Gotta love that shit. Be careful when there's e's, because people, when I put a 0 in, is this 0?
No.
Oh shit, so when there's e's in there, you gotta be careful. Don't just assume it's going to 0, because it ain't. Right, you do the 0 to 1, oh shit. So what is v of t? 3t squared plus 4t minus 6. Kick ass. And now you try to do you work it all the way back up to s of t. Do exactly what we just did until the end. Get what s of t is. No constants unknown. Oh, they made those nice. Oh, today's Wednesday. Good. All right, so this one's not too bad because the numbers they gave us are nice. So I get s of t is
T plus 2t squared minus 6.
yeah, good. It's even 1. Now, technically, you shouldn't use c because we know c is negative 6. So even if it's not really there anymore, it is sort of there in the problem. So use the next letter. Or you use C1, C2, whatever the hell you want to use. So just don't use the same thing you already used, because we know what that is. And so S of 0 is 9, means that D is 9. So then that's easy. Because 0 would just 0 everything out. That's the only thing left alive to equal 9, so that equals 9. Minus 6t plus 9. Ah! I like it. Not too bad, right? And again, the more you know your derivatives, the easier this kind of thing is. You're not going to see anything too intense as far as functions go, because there's only so many functions that we can do this with nicely. Why couldn't I do... Oh, this is evil. Well, the easiest one I can't do, for example, would be natural log of x. Because then you think, well, what do you take the derivative of to get natural log of x? And this is where people give me the wrong answer. They say, 1 over x. No, if you're thinking that, you're wrong. Because what do you do to the natural log to make it 1 over x? You take the derivative. And I'm asking you to take the antiderivative, so we currently cannot do that. You actually officially can't do this until the beginning of Calc 2.
What is the answer?
X ln x minus x. But what good does that do? I'd rather be able to do it, right? It's not obvious, is it? Well, here. Take the derivative of this. What do you get?
ln x
It would be ln x.
minus 1.
Yeah.
You still have the product rule.
Product rule.
Minus
Plus x times 1 over x is 1.
That's 1 minus.
Minus 1. There you go. So what is the antiderivative of this? It must have been that, because that's what I took the derivative of to get this. Do you guys get the relationship here, right?
Yes.
If I take the derivative of something to get a function, the antiderivative of that function must have been what I took the derivative of. Let that be just a definition, because it is, right? Nothing to realize, is just the definition of what you're doing. I love you guys. Some of you guys look angry at me always, but I'm trying not to take it personally.
What about logarithm?
Like that one?
No, not natural one. Just log.
Well, logs are even worse, right? Right? They'd have to involve, but they're not as bad as they could be, because they would just have an extra constant floating around, right? Okay. But, I mean, what about this one? It's really easy to make something that doesn't work. Can you do the antiderivative of that? That's going to be really bad. right? And this is where you're still not sure what to feel about this, because you would think, your brain would say product rule, but what's product rule work for? Derivatives. Antiderivatives don't have those rules. They have different rules, because it's the backwards thing, so it's not going to work the same way. Do you guys kind of see what I'm saying? So for example, what is the derivative of that?
Sin x plus x.
Plus
X
x cosine x. I like it. So then the antiderivative of this
Negative.
is this, right? Is that obvious? Hell no. You guys kind of with me? So antiderivatives will always be more difficult than an associated derivative could ever be. Because antiderivatives is the opposite. It's trying to undo differentiation. So we have a product rule that breaks things up. So antiderivatives somehow has to put them back together. Holy shit. Right? And that's not going to be a product rule. That's going to be something else. Right? Or a procedure that we have to follow. Are you guys semi with me? So in section 4.9, I want to make sure I get you guys to understand. 4.9, they're not going to give you a function that you can't do. They're going to give you something you can think backwards about. I just want you to realize that the story is bigger, and that's why we don't stop at 4.9 and say, you know all of calculus. It actually bleeds over into the next calculus level, just dealing with undifferentiated antiderivatives, right? Okay, maybe. Okay. Blah, 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 blah. Just want to make sure there's nothing too weird for you guys in the homework. Too weird by my standards, by the way. Bless you. Oh, so if you get something like this, they want you to find big ass G if they give you this. What was it, Jeff? All right, something like that. Okay, bye.
Oh my god.
Oh, you guys are so funny. No matter what you're doing, if you're about to apply a process to a function, what have we learned we look for first? Can you simplify it, right?
1 plus.
So, let's do this. We're going to need something to help us do this. We're going to need a more...
Is that a 1t or a 1 plus t? 1 plus t.
1 plus t. My t's are hooked at the bottom, right?
1 plus t plus t.
Let me overdo it. Let's make it x. Is it better? No capital T. There's supposed to be a big plus sign. Alright, now stay with me now. You guys might realize what I'm asking you to do here. Just simplify the damn thing, right? That's what you always try first. You simplify it. So what do we just say? If I have f is x to the fourth, what will f, big ass f be? What will the antiderivative be? And do you see how, didn't I have to figure out what the power was first?
Yes.
And you figure the power out by undoing derivatives. What do derivatives do? They make the power go down by 1. So what do? We make it go up by 1. Oh, expensive. Because we're doing the opposite thing, right? And then once we know the power, we put 1 over that power. And then plus c. I like that. So, in general, if I have x to the n, what's big ass f going to be?
N plus 1 over n plus 1 plus c.
It was up there before.
Oh.
I don't know if you remember that. They used a symbol we don't know yet, but it basically a symbol. This symbol, if you see this symbol, we still need to make this connection, but it's going to mean the antiderivative of something. So I can represent this as the antiderivative of x to the n with respect to x is this. Okay, so there's our first antiderivative rule. And it's the first derivative rule we learned in reverse. It makes sense. Right? The power rule is the first thing we learned for our derivatives. Derivatives. So how do I do this then? The first thing I do is what? What do I get here?
X to the
X to the
negative
-1/2.
plus x to the 1/2.
X to the 1/2.
X to the 3
3/2. I have a whole other x, so it's one whole x bigger. I just stopped there for a second. I mean, that's what I would do to take a derivative. So it actually is the same thing I do now that I have a rule that works on things that look like polynomials for antiderivatives. That's what I try to make things look like. It's the simplest rule. Right now, it's the only damn rule we know. So then what's big ass G? It's what I love. Well, let's see.
So it's going to be x to the 1/2.
Yes, good. And the shortcut, I don't remember. Remember we were doing derivatives? I said the shortcut was -1 minus 2. Now, so now when you're taking the antiderivative, you do -1 plus 2. It's crazy. -1 plus 2 is 1 over 2. So it's going to become x to the 1/2. Now what must have been out front, or just using the rule,
2.
it's going to be the reciprocal of this. All right, let me stop there for a second. I've used the rule. I made that go up by 1, and then I divided by what that became, which is the reciprocal 1/2 is 2. You guys cool with that? A whole other way to look at it is, if I put a 1/2 there, a 1/2 would come down. There's no number, so there must have been a 2 there to kill that 1/2 that came down. That's another way to kind of think about it. Choose a way. All right.
Plus 2/3.
Yeah, it would be x to the 3/2, and then the reciprocal
2/3.
2/3. I like it. X to the, that's right, 5/2,
2/5.
and the reciprocal 2/5.
Plus C.
Plus C. Cool. So that would be the antiderivative of that, which is that. Bless you. What is that? It's like a jazz thing. Okay. Alright, so that's that. Yes?
Is that is the last one to the 3/2?
5/2, sorry.
No, above that, GX. The little G.
Oh, definitely, because x squared divided by x to the 1/2.
Okay.
Subtract those powers, cool.
So over there, x sine x, it's just multiplication.
Here?
Yeah.
So my point for this was, the derivative of that is relatively easy. If I wanted to make the antiderivative of that, I don't know how to do it currently. And again, this would be one of the first things you learn in Calc 2. So we just started integrals, and I'm already telling you, we're going to learn up to a point, and this function I just wrote down, which is relatively easy to do the derivative of, you won't know how to do it at the end of the semester, I'm sorry. So if you don't take 280, you might never know. You just got to look on YouTube, though. I'm sure somebody made a video out of it. Okay, all right. Let me see. That's the only real official rule we have so far for integration. On page 345, if you have your book or will have your book, they list some. So, I mean, for example, this is just, do you know your derivatives? If I said f was secant squared, what was big ass f? Yeah, so it's really just asking you the derivative of what is secant squared. I mean, that's really what antiderivatives are at their heart, right? All right, good. Nothing really more than that, but we're going to develop rules to help when there's more shit going on. Okay. I like it. 345. Oh, sorry. Thank you. Yeah, page 345. All right. So that's all I want to say right now for about 4:9. We're going to get into chapter 5. Look at you all like, is he going to let us go? No. It's Wednesday. You're mine for longer. Okay. So I mentioned earlier there's a process that finds areas under curves. And okay. Let me see. Let me start with the easier one, and then I'm going to show you something I came up with on my own that I'm really curious now if anybody's ever done this. So I don't know how that makes you feel, but I really don't care. It's really cool. Let me see if you guys agree with me or not. So the first thing I want to show you is something I don't know if anybody's ever seen this, but if I want to, that's pretty good for you. If I want to find the area of a shape. Let's pretend like we don't know the area of a circle. And I want to find the area of a circle. What I try to do is reposition it so it looks like a shape that I do know the area for. You guys kind of with me. So for example, if I have a parallelogram, I could cut part of it off and put it over there and make it into a rectangle, right? And that sometimes is the way that that's presented. I don't know if you guys are with me or not. So for example, what do you think I'd call that? The height. That's crazy. And this would be the base here, right?
Yeah.
So if I cut this triangle off and put it here, I've made a rectangle, right? And this would be the original base would be here now, right? So the area would be height times base. So what's the area of a parallelogram? The actual height times the base. So I can formulate an area for a new shape if I reorganize the area into a shape that I already know. Because if I just move parts around, have I changed the area of it?
No.
Thank you. Okay, good. Right? I haven't changed the areas. I've maintained the areas. So it's got to be the same area as it was before. So I don't know if anybody's ever seen what you can do with a circle. That's kind of neat.
Trapezoid?
No. You're thinking about that one problem in homework. No. If I cut it down the middle. First off, let me ask you, how far is it? Let's call this radius r. Right? We'll call that radius r. So how far around the whole thing is it? What's the circumference of a circle? 2 pi r. So how far is this? Pi r. Kick ass. All right, let's start there. Kick ass. And it's green zoom. So here's the idea. If I cut triangles, not through that edge, but to that edge, so then I could do this with it, pick it up, and put it down like this. Can you guys see that? I didn't count the triangles, I don't know if again, but that's the idea. You with me? No, you had 7. Second?
They make little arches, right? On the bottom of the triangle. Like if you pull it out, there's still like little arcs.
No, you can flatten this. Is that what you mean? You can
Yeah.
totally flatten that.
But I mean, the bottom would still be like an arc, though, right?
Oh,
The triangle's not going to go all the way to the edge.
exactly. So what I'm about to do is, what I'm doing is going to become better the more triangles you use, which leads beautifully up into what we do to find areas. So stay with me. You guys are like, what the hell's this shit about? So you can imagine I'm going to do the same thing with the bottom. Open it and then fit it in. So how long is this? Pi r. Yeah, it's this. Opened up. Right? And then if I fit these and fit them in, how tall is this? Especially if I use a lot of triangles. If I use a lot of triangles and get better resolution, this is going to be r, isn't it? It's going to be r tall. And now I've made a rectangle pi, right? R. So what's the area of this rectangle? Pi r squared. Hey, shit. Has anybody ever seen that?
No, I'm not.
Isn't that kick-ass cool, though? I show that to my, whatever class I'm talking about, area of a circle. I show that to them real quick, and they're all like, holy crap. It's really kind of a cool visual, right? I'm not the kind of guy that would bring construction paper and actually do it, but if you wanted to. All right. So that's one thing to realize. And this kind of thing works, not exactly this kind of thing, but this idea of reorganizing an unknown area into a shape that you know the area of. Whatever the formula is for that is the formula for the thing you had originally, because it's the same freaking area. That's how you make the area of the trapezoid. You cut it into 2 triangles, and then you add those 2 triangles, and you get the area of the trapezoid. Woo! Okay. Second thing is the new thing. Let's see what you guys think about this. This gets a little bit nifty. Another circle, not as good as the first one. Well, it's got mumps or something. Let's say it's got a diameter of 10. Now this is I like these 2 examples together. You'll know what I mean better if we get into the idea. I can overestimate the area of this circle by drawing a square that the circle sits in, right? Do you guys kind of see what I'm saying? if I draw a square that meets it at these points, pretend like it's a square.
So the diameter.
Well, that's a lot of imagination, but oh well. Don't kick the baby. No, get away.
So the diameter will become
Yeah, so what's the area of this purple square?
100.
I like it. So it would be 10 by 10 kick-ass. So that overestimates it, right? Whatever the area of the circle is, it's less than 100. Are you guys with me on that? So how could I underestimate? Probably do the same kind of thing, except I'm going to put the square inside. I like it. So that's obviously going to underestimate the... Now, this is going to be a little bit more of a challenge, which normally translates to crappy picture, but I won't. Jeff, just let it go, dude. It's all right. You'll be all right. All right. Pretend it's a square. Now, what do you know about anything about the square's dimensions? Do we know anything about the square's dimensions?
They're all
I like it. It's a square, so the sides are all equal. I'll allow it because I opened the door for that. Maybe something a little less obvious. Diagonal is the diameter. I love it. Isn't the diagonal going from one part side of the circle to the other? So that is 10. Across there, that's 10. Yay. So how does that help me? I don't know. Well, let's break this down. So then what are these sides then going to be? I don't know if you guys remember. What do you think these angles are here, considering it's a square that it just chopped? 45. So does anybody remember anything about 45, 45, 90? Do we have to go all the way back to trig and use trig? No, we shouldn't. We should just be able to use ideas.
Is it 10 over square root of 2?
There it is, yeah, 10 over add 2, right? If it was a unit circle, what would the sine of 45 degrees be, which is the length of this side? What's the sine of 45? Sine of 45? Oh, shit.
Square root of 2 over 2.
1 over rad 2, basically, right? Just rad 2 over 2, but 1 over rad 2. You guys with me? So it's 10 times as big, so it's 10 over rad 2 for that side, 10 over rad 2 for that side. Over, Jeff, you can do it. There you go. So what's the area of the red square? 100 over 2. Square root of 4.
So it's
100 over 2, so what's 50. What's the average of those two? Does it make sense? Why would I take the average? Because the red one underestimates the area, and the purple one overestimates. So the average should come out to be an okay estimate.
So, I mean, it's like we are cutting, right?
We're not cutting. We're actually just... You have a circle, I'm going to overestimate it, I'm going to underestimate it, and then take an average. So it's a very crude procedure, but it's actually the same procedure we use for functions. We just have a control on how to make the resolution better. Here I don't have a control on how to make the resolution better, really. So what's the average of those two? So the area of my guess is 75. Now what is the area of that circle? Area is pi r squared. What's the radius? 5. 25 times pi is a little over 75, right? It's actually 77 point something?
78.
78? Okay. So, was our guess pretty good? Shit, yeah, man. If we were a civilization that had not come up with this formula yet, that guess is pretty damn good for us. Okay. So, here's the idea of what we're actually going to be doing. So, these two together, cutting an area up into a shape that you know, and over and underestimating and then taking an average. Somehow that plays into what we're going to do. Okay. I'm excited. This is the first time I ever introduced this like this, and I think these two examples are really good. So we'll see. I don't know. So let's try a simple... Oh, beautiful. Get some time. A simple function. Let's say... What you got, Jeff? Well, let's just do 1 over x. From 1 to 4. I like it. So to graph a rough sketch, at 1, where's 1 over x? 1. And at 4, it's at 1/4. That's crazy. That's a horrible scale, but 1/4. And of course at, here we got 2, 3. At 2, it's what?
1/2.
1/2, and a 3 is a 1/3. So it's like, okay. So what I want to find is the area. So now the actual function itself goes off in both directions, but this just says the area from 1 to 4. That's what I want to find. I want to find this area, right? Let me take this out of there. Get up. You can draw stuff in there. Go away. So here's the idea. Merging the two things. Chopping it up into shapes that we know, while at the same time over or underestimating. That's what this process really is. So what I'm going to use are rectangles, because rectangles, remarkably simple area formulas, right? There are processes that you learn in Calc 2 where you use trapezoids and you use parabolas and stuff, Nito stuff, right? Engineers have to use that kind of stuff. Oh yeah. So if you're an engineer and you got to take Calc 2, and there you go. That's one good reason. And you're like, we got software, screw. So if I want to use, let's say I want to use 3 rectangles. I'm going to make it nice just because this is our first example. So if I want to use 3 rectangles to estimate that area, how wide must each of my rectangles be?
1.
1, yeah, because they got to go from 4 to 1. And I want to use 3, so they got to be 1. So the width, I'm going to use delta x to represent the width. That kind of makes sense because it's going to be on the x-axis. This is how much x changes for each rectangle. So in general, the delta x is going to be the top minus the bottom divided by the number of rectangles I want to use, right? So if I wanted to use 6